we're going to derive the step response for the series LC circuit in the frequency domain. So I have done the Laplace transform uh, in both voltage source analogy and current source analogy. We're going to apply both KVL and KCL. So here, so by KVL we get here in this circuit, so SL plus 1 by SC IS equals Vs by S plus LIO minus VO by S. This VO by S. So this will give us, so 1 by SC S square LC plus 1. Now Vs by S plus LIO minus VO by S. If we just rearrange this, S square LC plus 1 IS Vs, so C plus SLC IO minus CVO. This gives us IS Vs by S square plus 1 by, so we are gonna assume omega n is 1 by root over LC here too. So LCL plus IO S by S square plus 1 by LC minus VO by L 1 by S square plus 1 by LC. Hope I hope you understand what I have done here. So IS equals to Vs by omega n L omega n by S square plus omega n squared plus IO S by, so this is the situation here. Now if we just apply the inverse Laplace, it will give us IT, which is, let me write this in let me write this like this. So cos omega nt, this part, minus VO by omega n L sin omega nt, the inverse Laplace transform this term, and plus Vs by omega n L sin omega nt. So this is the current response in frequency domain. So I don't know if I have made a mistakes So this is basically it. Now we apply KCL in this circuit. Here we can see that at this node volt at this node the voltage Vs is 1 by S Vs by SL plus SC Vs equals to 1 2 3. So Is, assuming the current direction given, I have assumed here, Is by S minus initial current by S. This is the initial current IO by S plus CVO. Now V is S square LC plus 1, and taking the SL, the common SL term out, so and multiplying it in the right hand side. So Is SL by S, this cuts out, minus IO by S SL, this cuts out also, plus SLCVO. V is equals to Is L by S square plus 1 by LC common, minus IO by S square plus 1 by LC common. Here's an L plus SLCVO by S square plus 1 by LC common. This cuts out, cuts out, cuts out, leaving behind, say, Is by, take an omega n by S square plus omega n square. Omega n is 1 by root LC, minus IO by omega nc, omega n by S square plus omega n squared, plus VO S by S square plus omega n squared. So here we have found, now we are in this stage. So when we are applying the KCL, we have assumed the step input a current source, but in actuality, so we are gonna represent this Is in terms of voltage. So how we are gonna do that? So we know that Is is Vs by omega nl or Vs omega nc. We're gonna use each either of these two formula. Vs, the bigger Vs, the voltage response in frequency domain. First, let me um, represent this term uh, in terms of voltage. So Is by omega nc, omega n by c square plus omega n square, which is, say, I'm gonna use this Vs by omega nl for convenience, obviously. So Vs by omega n sorry, this is is equals to vs by sl equals to vs sc. So this will be sl and vs sc, not omega nl. Okay, so omega n s lc omega n by s square plus omega n square. Now what we're gonna do is, so vs by s into s square plus omega n square, and here let us take the partial fraction of this. So a by s plus bs plus c by s square plus omega n squared. Now we have to take the partial fraction. So here is an omega n square. So to get the arbitrary constants, so omega n square equals a s square plus omega n squared plus b s square plus cs. Say s is 0, which will give us a omega n square equals this two terms will be 0. So omega n squared a equals 1, which is plus 1. Say we don't have to assume anything now. Now let us equate the coefficient. The equate the coefficient of s square and s. So if we equate the coefficients of s squared, we will get a plus b equals 0, which will give us b equals minus a equals minus 1. And if we equate the coefficients of s, it will only give us c equals 0. So we have got our all the terms. A equals plus 1, b equals minus 1, c is 0. Now vs, so a is 1 by s, plus minus s plus 0 by s square plus omega n squared. This is vs 1 by s minus s by s squared plus omega n squared. So this is the real input voltage term in the frequency domain, and we're gonna use this to get the frequency domain response of the voltage of the LC circuit, the voltage response in frequency domain. Here we have used the current source, but in actuality we have connected the DC voltage source with the series LC circuit. So we have to represent this current source in terms of voltage. So we have assumed that magnitude is Vs by impedance. Here impedance may be SL or Vs SC. So we have assumed this too. Now V as the voltage response is Vs 1 by S minus S by S square plus omega n squared minus Vo S by S square plus omega n squared. So this is plus minus Io by omega nc omega n by S square plus omega n square. So we are gonna take the inverse Laplace of Vs. This will give us time domain response, and here Vs, this is 1 minus, this is cos omega nt cos omega nt plus Vo cos omega nt minus Io by omega nc sine omega nt. So if we just rearrange this, it will give Vo cos omega nt minus Io by omega nc sine omega nt plus Vs 1 minus cos omega nt. So this is the answer. This is the voltage response of the series LC circuit to a step input or DC input. So after analyzing the series LC circuit with step input in both time domain and frequency domain, we found our complete response. The main response is the voltage, which is Vt equals Vo cos omega nt minus Io omega nc sine omega nt plus Vs 1 minus cos omega nt and it, if you wanna write this, so Io cos omega nt minus Vo by omega nl sine omega nt plus Vs by omega nl sine omega nt. So this is the complete response of the series LC circuit, complete step response of the LC circuit. I think there was some plus minus issue in the time domain. You can see this yourself if you find anything, but I think basically this is the answer, and that's it.